In this session, I'm going to learn how to convert a Cauchy problem to a Volterra's integral equation. In the previous video, we look at the general form, how to convert a first order Cauchy problem to a Volterra's equation, and that of the second order to a Volterra's integral equation. But in this session, we're going to consider some examples to explain what we did the last time. So this is our Cauchy problem. We are going to convert this Cauchy problem to a Volterra's integral equation. First, let's make the y prime the subject of the equation. So this y prime can be written as dy ds. Let's multiply through by what? ds. Now let's integrate both sides of the equation. Since we're converting to a Volterra's integral equation and the initial problem starts from 0, I'm going to integrate from 0 to s. So dy of, now we interchange here to t, which will be equal to integral of 0 to s. This is a linear operator. I can rewrite it as t dt plus integral of 0 to s y of t dt. If we multiply this by this, I'm going to get integral of what? S ds. But since we are integrating from 0 to s, we change the s here to t and dt. The s here to what? T. That's why we're having this equation. If we integrate this side, we're going to get y of t evaluated at 0 to what? S, which will be equal to t squared. If we integrate t, I'm going to get t squared over 2 evaluated at 0 to s plus integral of 0 to what? S, y of t dt. Now we're going to have y of s minus y of 0 to be equal to s squared over 2. If you put 0 here, it's still 0. So plus integral from 0 to s y of t dt. And our initial condition here is giving us what? Y of 0 is equal to 0. So here becomes, the resulting equation becomes y of s to be equal to s squared divided by 2 plus integral from 0 to s y of t dt. So we're able to convert this Cauchy problem, which is y prime minus y equal to s, with the initial condition y of 0 equal to 0, to this integral equation. This is an integral equation because the unknown function appears under the integral sign, and this s squared divided by 2 is a free term or the forcing term. And we are integrating from 0 to s, which makes it to be a Volterra's integral equation. So let's consider the next example. example, we have when y prime prime plus 5y prime plus 6y equal to 0. With the initial conditions, y of 0 equal to 1 and y prime of 0 is equal to what? 1. And this same equation can be written as d square y over the s square plus 5 dy ds plus 6y equal to what? 0. Now you take the differential operator with the highest degree. So the highest degree is here is d square y dy square. Now let the d square y over the s square to be equal to another unknown function. Let's say u of s. This equation can be rewritten as d ds into bracket y prime of s, which is equal to u of s. This equation can be rewritten as which is equal to u of s ds. Now let's integrate both sides. Since it's a Volterra's integral equation and the initial condition starts from 0, so we are going to integrate from 0 to s. Since we are using s here, that means we need to change the variable here to another variable for better communication. So we are going to have dy prime of t, which is equal to integral from 0 to s u of t dt. Now if we integrate this side, we are going to have y prime of t evaluated from 0 to s, which is equal to 0 to s u of t dt. So we are going to have u prime of s minus u prime of 0, which is equal to integral 0 to s u of t dt. And our u of 0 was given as 1 and u prime of 0 was also given as 2. So our u prime of 0 is 2. So I have our u prime of 0 here. And we are going to have u prime of s minus 2, which will be equal to this. Now let's make u prime of s the subject of the equation. The resulting equation becomes y prime of s, which is equal to 2 plus integral from 0 to s u of t dt. Let's name here as our equation 2. Our first equation was d square y ds squared, which was equal to what? U of what? S was our first equation. We now have for y prime remaining y. We need to look for y. Now to look for y, we need to integrate this equation. So we have y prime of s to be equal to 2 plus integral from 0 to s u of t dt. So this is the same as dy ds, which is equal to 2 plus this integral from 0 to s u of t dt. So we still have our dy, which is the y is a function of s, which is equal to 2 ds. If we multiply each of the term by the ds plus integral from 0 to s u of t dt ds. Now let's integrate each of the term. Now let's integrate each of the term from 0 to s. So integral from 0 to s, the y of t, like changing the variable here again, which is equal to integral from 0 to s to dt. There's s in, so you have to change it to a dt, plus this integral from 0 to s, then integral from 0 to s. We're having our u of t dt dt. This s is changed to a t. Now, if we integrate this side, we're going to get y of t evaluated at 0 to what? S, which is equal to, if we integrate 2, we're going to get 2t evaluated from 0 to what? S plus, and this is a double integral, and the term we had, the note we had in the previous note, it says that you count the integrals, which is 1, 2. So we are, the n is equal to 2. So we're going to have 1 over 2 minus 1 factorial, integral from 0 to s, and s minus t, 2 minus 1, u of t dt. Now this this double integral becomes a single integral. If we evaluate this one, we're going to get y of s minus y of 0 to be equal to 2s minus 2 times 0 is still 0. So plus integral from 0 to s, then s minus t, then 2 minus 1 is 1. So s minus t, u of t, then dt. And from the initial conditions, we're having y of 0 to be equal to 1. So let's substitute the y of 0 here. We're going to have y of s minus 1 to be equal to 2s plus integral from 0 to s, s minus t, u of t dt. Now let's make y of s the subject of the equation. We're going to have our y of s to be equal to 1 plus 2s plus integral from 0 to what? S minus t, u of t dt. And let's name this equation as our equation 3. Now we are having our equation 1, which is y prime prime, and equation 2, which is y prime, and equation 3, which is also the y. Now let's substitute equation 1, 2, 3 into this equation note, into our what? ODE. So our y prime prime is u of s. So we are having u of s here plus 5. Then y prime of s is equal to this, which is into bracket 2 plus integral from 0 to s, u of t dt. And next one is 6 plus 6 to bracket, then our equation what? 3, which is giving us 1 plus 2s plus integral from 0 to s, s minus t, u of t dt. U of t dt. Now let's do our algebra here. This is the same as u of s plus 5 times 2. We're going to have 10 plus, yes, 5. So 5 is a constant. Can I just bring it inside the integral sign? Since integration is what? A linear operator. And it's a constant to 0 to s 5 u of t dt plus 6 times 1. I'm going to have 6 plus 6 times 2, which is what? 12s plus this 6 times the whole of this. I'm going to have integral from 0 to s, 6 into bracket s minus t u of t dt, which is equal to 0. The whole of this is equal to 0. Now you can add 10 plus what? 6, which will give me 16. We're going to have u of s plus 16 plus this 10, which is 12s. Then we're having this integral sign. You can combine these two integral signs. Now we're going to have plus integral from 0 to s, then 5 into bracket 5 plus 6 s minus t, then you close the bracket times u of what? T dt, which is equal to 0. Now let's make our u of s the subject of this equation. And I'm going to have our u of s. We're going to have our u of s to be equal to minus 16 minus 12s. Then we send the integral sign to the other side, which is minus integral from 0 to s to bracket 5 plus 6s minus t bracket close, then u of t dt. So we are able to convert this ODE with its initial condition to this integral equation. We are seeing this integral equation because this is our unknown function, and the unknown function also appears under the integral sign here. And we are integrating from 0 to s, so it makes this equation to be a Volterra's integral equation. So this will be the end for the examples.